You're good to go.
Right, okay. Hi, I'm Michael Bane. I'm from Manchester Metropolitan University, just down the road from the University of Manchester. I'm going to talk about three things in reverse order, a little bit about my research and some of the social science aspects of getting to net zero, a specific project that we're working on looking at challenges of energy monitoring and reporting, particularly for heterogeneous systems. And this is a kind of sub-project of the UKRI DRI scoping project, which is what I'm going to kick off with. So just a bit of motivation. As we know, the IPCC is essentially a climate emergency. We need to get net zero. We need to reduce our emissions drastically and quickly. And it's good to see the last of today's workshop have a theme all about sustainability and net zero. By net zero, I think we all agree, know that we're trying to get to doing stuff about actually having a net release of carbon or carbon dioxide or impact on the environment. We can see, I mean, numbers are quite hard to get hold of. Here's what I consider a very good estimate in Science 2020, where they're looking at how the number of servers and map storage, etc., has increased over the years 2010 to 2018, and you can see it's gone up by quite a high fraction. However, the efficiency of each of these units has also increased. The average PUE of the data center, for example, the number of servers on workload, have all increased the energy efficiency, such that we see, according to the authors, a total energy per year in 2010, 194 terawatt hours, only increased to 205 in that 8-year period. So it's not doubling up as maybe the number of instances double. It's going up, and it's estimated to be 1% global electricity use. These numbers are very, very hard to quantify. I've seen numbers for the UK that say the total compute ICT footprint of the UK is as high as 12% of the total energy use in the UK. Whatever it is, we need to reduce it. And UKRI is a government body that incorporates all the research councils and people like Innovate UK to fund a lot of the research that goes on in the UK, arts and humanities as well as traditional science as well. And the government has a target of net zero economy, net zero by 2050. UKRI is trying to get there by 2040. And they've funded this project called UKRI Net Zero Digital Research Infrastructure Scoping Project. I am not on the steering committee of that, but this is part of the presentations done on their behalf, and the slides provided by them, etc. So I'll talk a bit about this, and how projects like Alistair's just talked about, and what Jamie will talk about in a minute, all kind of fit in. So the idea of the scoping project is to come up with plans to help all of the digital tools within the UKRI environment become carbon neutral. And one of the key things to come up with is an interim report, and I'll give you my personal view on that. And then I'll move on to the specific project that's been funded as part of this scoping project that I'm involved in, that's called Energetic. So, first of all, DRI, Digital Research Infrastructure. As far as the scoping project is concerned, they're looking at the carbon footprint from everything from mobile phones right up to HPC facilities. It's a £1.9 million project, funded by NERC, ends next summer, and it's to get a roadmap to how UKRI could become carbon neutral. So it's not going to put in the plans, it's to influence the decision makers at UKRI about what policies it could put in place in order to meet their stated target. The project's led by the Centre for Environment Data Analysis and National Centre for Atmospheric Science, and it comprises two types of projects: consortium hub projects and various bespoke projects. So the ambition is to get this evidence to inform the policy makers and to come up with a potential roadmap or a choice of options for a roadmap, and also to lead to ensure there's a positive and leading role in people wanting to transform to a sustainable economy. So the hub projects and spoke projects. Hub projects are the main consortium within this scoping project, and there's 9 of these, including the ones we've just heard about from Alistair. So some of these projects about mapping the existing infrastructure, what is actually in the estate, what's the proportion of those, what kind of HPC facilities, tier 1, tier 2, what people might have in cupboards and things like that. And the specifics, like the very interesting about what Archer 2 and Cosmos are doing, but also other tier 1, tier 2 machines like Jasmine, Starfell, Pike, Archer we heard from earlier, and Jade. There's been an in-depth survey for users and system administrators about what do you think you can already get out in terms of energy or the carbon footprint? What would you like to see get out? And what are the barriers to you being able to get this kind of information? What would you like to see government do in order to improve the situation? There's been a very in-depth literature survey by the main consortium, and this has led to an interim report with various recommendations that I'll go through very shortly. And alongside that, there was a sandpit held in distant memory, from which 7 projects were funded. These are very short-lived projects, 5-6 months, started in August, finished in December typically. And some are looking at what do we need to do to get researchers to buy into net zero? How do we audit things? What policy makers need to know? And some are a bit more hands-on techie, job efficiency, energy usage were heard about. And I'll tell you more about the energetic project, which is looking at FPGAs, GPUs, and CPUs, and the potential role for them shortly. So, there's an interim report out, littered, probably the right word, littered my talk with various QR codes. There's links here as well. I presume the slides will be available, so you can click on the link, click over on that. So the interim report, it starts off by suggesting that UKRI carbon footprint as a whole is comparable to a large UK university. We don't say which one, but we get an idea. And maybe the DRI would be a large department in that university. And it's gone on to highlight that the key emissions would be the use of electricity and the hardware, the embodied emissions that Alistair just alluded to being, I would say, probably near 20-30% and 10%, depending obviously on the life cycle, lifetime of your kit. And also, operational flights is particularly carbon intensive. So there's various categories in the executive summary. I'll save you reading it all. I will go through the key recommendations for the report. So this is to give you a feeling of what's going on with UKRI. These are my selected and abridged recommendations, which I honestly believe reflect the totality of what's in there, rather than, I will show you full list later, but you see why I've kind of abridged them. So, one is to understand the views of the research community and actually use that to inform future policy of how we can get somewhere. So, we also need to treat net zero target as something that concerns everyone takes seriously. So on a path, things like health and safety, not just a kind of secondary concern, but a primary concern. The main recommendations probably of interest to the audience, I have summarised here. So there is a recommendation to continue to invest in new infrastructure to do new science. So that's good news. But to also adopt any efficiencies in new technology. So if new chips are more efficient than previous chips, we need to make good use of that. And this needs to be backed up by appropriate training and support and the resources to do that. It doesn't quite go as far as saying upskilling people in support to FPGA or GPUs or neuromorphic or quantum computing, but last thing that was in the mix as well. And then procurement, because as we saw, this could be a very large proportion of the the total carbon footprint. So, how to include sustainability clauses when you're doing procurement, ensuring you look at the full supply line, everyone down the chain, what are their carbon footprints and how can they reduce them? What influence do you have on them? How do you take account of them? And the whole life cycle analysis. Once a machine has got to that point where it's just not worth keeping, how do you dispose of it? What happens at decommissioning? What's the carbon footprint at that point and how could you reduce it? As Alistair was talking about, and I would say, whatever you do, you're going to end up burning some carbon. So how do you offset? How do you make that net zero? You can use renewables. And the recommendation is to also immediately implement offsetting, the stuff that you can't cover, and then move towards sequestration, where you're going to actually capture the carbon before it gets released. And reduce travel, particularly flights, do more things like Zoom, like this. So there's a whole load in there that's kind of relevant to today's meeting. This is the full list. It's available on the report from UKRI gave you earlier if you want to see more. And there's lots of opportunity for people to get involved. There is the Computing Insight Conference in Manchester, 2nd December, run by STFC. You can still sign up. And on Friday the 2nd December, there's a morning preliminary where everyone will be, where there'll be some presentations from the consortium and the sandpit projects I've just kind of quickly outlined, and a panel discussion things what I'm looking forward to shortly. And then in the afternoon, there's a specific workshop about how do we measure energy on these systems, particularly heterogeneous systems. How do we standardize that? And this is the energetic project that my last slides will be covering. UKRI will also be having an engagement workshop for all the different elements of UKRI. That detail's not public yet, but that will be in May 2023. People are invited to come along and have a say and discussion at that point. And to keep more up to date with the mailing list, at the bottom of your specific questions and email address as well. So one of the sub-projects funded by the scoping project is energetic, and it's a very strange acronym for energy-aware heterogeneous computing at scale. So there's a couple of things that we're aiming to do in this. Bearing in mind it's quite a short project. We want to look at how to measure report energy in a standardized manner, and we want to look at accelerators, GPUs and FPGAs. Particularly we want to test the hypothesis that the use of heterogeneous computing makes significant energy savings. And this will help influence future policy if we can show the FPGAs that do the science and they can do it with much less energy as a solution, then it's worth investing in expertise in order to perform to them. Conversely, without saving any energy, why bother? So the main thing that I'm going to cover after I spend my time on all the energy measurement stuff, and this will be an overview of some of the things that we're looking at and some of the challenges ahead. So the project started in August, holiday season finishes in December, holiday season, so we're about halfway. And these are the people working on it. PI, Oliver from Edinburgh, Jamie from UCL will be talking after me, and DPN and Tamor from Newcastle. So a total of 7.5 months of effort, not a huge deal. And as we do it, we're finding there's more and more questions. So in some ways, we could break down how you can measure the energy. You can say on a compute node, so we've heard a little bit about this, we can do it up to cluster level. What we're really interested in is at the data center level, the total carbon footprint of running that data center. The compute nodes, the cooling, the network, the disk, any other infrastructure. That is what's going to contribute to climate change. What we typically measure, going one way, is what goes on at compute level. So users typically look at this. How are we going to obtain the energy data directly, how accurate are these measurements, and is their resolution sufficient? So for CPUs, we could use hardware counters such as RAPL, that also gives us energy consumption of the memory. Some of these might give us power consumption and integrate over time. It's energy that we actually is the metric that we're interested in. But how do you do the rest of the node? What about the disk? What about the inefficiencies of the power supply unit? Does it have I2C? So maybe we can measure that. And more interestingly, what do you do about accelerating the end of the PCI Express? So to answer some of these questions, how accurate are the measurements that we can get? Is the resolution sufficient? We've got ourselves a high-end data logger, and we'll be doing some intrusive measurements, and we can compare this to what we can see from the likes of the software that exposes the hardware counter data. But we've got to bear in mind that, RAPL isn't just the answer. They're only going to work with CPUs, what we're going to do about accelerators. On some systems, hardware counters aren't always accessible in user space, so what do we do about that? And how do we get to this single software in user space that's going to give us accurate data on the energy, whatever the architecture? So there are some wrappers, some tools available. We're doing a survey of these, seeing how they work. We're looking at things like Happy, Liquid, and then there'll be some vendor-specific, typically GUI-based things like Intel's Amplifier V2, what we call it today, and Microsoft from AMD. And it's important also to kind of put this in context of other initiatives, particularly from the labs out in the States, things like UKRI, PowerStack, and Intel-backed GeoPM. So we'll be looking and comparing these, and also looking at what are the challenges for system managers in order to expose this data at some level to users. Is it just in batch jobs like we heard earlier, or are there other ways? What's needed and what's possible? We're currently using Happy and Liquid. But this is only a first approximation, remember, in that where this approach only measures the computer, we want to know the total data center carbon footprint, and indeed how to reduce it. So the project isn't just about CPUs, it's about accelerators, GPUs, and FPGAs. So that brings another level of questions. How do we get a standardized approach to get the total energy for an application across all of these different components, whatever the make of GPU or FPGA? And then we get into the more, well, not more interesting. Another interesting field is, well, once you work out, yeah, it's worth using GPU and or FPGA, how are you going to balance the number of cores and the number of GPU cores, the number of threads per block on the GPU, how many FPGAs, in order to find the global minimum of energy to solution? You don't want to run every single possible configuration because you just burn too much energy trying to find the minimum. And also, you've got to bear in mind that if we offload stuff to a GPU or an FPGA, the idle draw of the CPU is non-zero, significantly in some cases, so we need to kind of put that into the equation as well. So what we've learned so far is there is an imperative to have joined-up approach to measuring energy consumption across the whole set of components, but also to see where that energy has been spent. Has it been on this accelerator or that accelerator or CPU? We're aiming, to come up with something like this quadrant of energy. So we'll be able to say what type of codes are easy to pull, going towards the right, and also give good energy savings compared to just the CPU implementations that are going on. So the top right-hand quadrant is what we want. Lots of codes in there that would be giving good energy savings, but not too hard to pull. Bottom left, kind of really hard to pull, not so much savings. Those are codes we can top them to do something with. As I said, we need to find the right mix of number of CPU cores, GPU cores, FPGA kernels. Then we've got to bear in mind data transfers, multiple nodes, and so on. And that's before we start thinking about varying the voltage or varying the precision. Some of this won't be possible with the small amount of effort we've got to do the chat. So that's fine. I've got a box there for all this kit myself. But what happens back cloud? So some of the challenges will be the same. Does the user have access to the relevant hardware challenges? But what about if we've got several VMs on one physical machine? How do we account for that? How do we know the actual equivalent of the data center footprint? We don't know anything about how the different cloud vendors cool their systems, how efficient they are. So there's a lot of more information that's needed there. And what happens if you've got code that auto scales? How do you capture that automatically? I'd like to think that rather than cloud vendors competing on price, maybe they start competing on least carbon per simulation, least carbon per analysis, etc. Why don't we know what the carbon footprint of an instance is? And this all leads on to my more personal view, I would say, that what we really need is a paradigm shift. Forget time, forget money, it's only carbon. We're serious about net zero, then it's only carbon. So research councils, funders, etc. Why not bin monetary budget, financial budget? Just have carbon budget. And then users, instead of saying, I'd like to spend so much money, have to make the case for how much carbon or carbon dioxide they need to create. In terms of people running systems, the default could be, have a smart scheduler, I'll talk about that in a minute, that has a configuration for a given code that produces the least carbon. It might mean it takes longer to run. It might mean it won't even start running until night time when cooling might be passive and your efficiency of your data center increases. If that's the default, that helps push down the total energy usage, total carbon of a given data center. But of course, people say, oh, well, I really need it now. Then they could pay some penalty for that. But why not make the default least carbon rather than scheduling for run as soon as possible? So in terms of, this all kind of fits into my research. You want to measure stuff, but you also want to be able to predict stuff. You don't want to have to do 100,000 data points to find the minimum. You want to run a model that will tell you what the minimum is. Have a look at emerging technologies. What's the energy footprint of quantum computing compared to GPU? So let's have a look at that. We're also looking at machine learning to find the optimum compiler settings and the optimum runtime option, number of threads, etc., to run a given code, optimal being the least energy solution. We're hoping to, with an EPSO grant, advance that to also cover accelerators. And then smart scheduling. I've not mentioned AI particularly so far, but this is all in this one phrase. So if we want paradigm shift to where carbon matters and if the job is going to run in a state where it produces the least carbon, why don't we work towards having a smart scheduler that can do all this? We want to automate it as much as possible. The user submits a code, scheduler, smart scheduler will decide whether it needs recompiling so it can find a lower energy solution. It will decide whether to run it at night time, whether there might be less cooling in the data center, decide the optimal number of nodes, etc. But we could also move on to failed jobs, as Alistair saying that. A failed job is often just a waste of carbon, so if we have sufficiently advanced AI that say, oh, you've run that before, you don't need to run that, we could actually reduce the number of failed jobs. So there's a lot of research going on in this area at the moment. What I do think is we need this paradigm shift to move away from, oh, let's just run it now, or even worse, oh, I'll just run it one more time, see if it does the same thing. No, we've got to be serious if we want to get to net zero. We've got to stop just doing things. We've got to think about the energy footprint and actually make the case to do it rather than just do it without thinking. We could have systems. There's various examples where this kind of worked for different reasons in the past. And what do we need to do? This is social science. What do we need to do for people to actually think, yeah, I'm happy with carbon cap, and start thinking about their carbon footprint and stuff, making use of the information such as Durham and Co. and Archer are giving to their users. So that's it. I'm more than happy to take any questions.